Now let's see how to analyze a program which is containing some branch instructions in them, because of which our clocks per instruction is going to be more than one. Okay, so what I mean to say is, we know that clocks per instruction under ideal conditions has to be one in a pipeline organization, but because of the presence of some conditional branches or unconditional branches, because of the presence of the branch instructions, there will be some penalties, because of which, let us say, these penalties have not overcome by the compiler. Okay, let's discuss about it in a raw form. Recently what happened is, not to cover up these penalties, compilers are designed in a smart manner, in such a way that these penalties will be covered by some other instructions. But assume that we are not taking any support from compilers, and whenever there is a branch instruction, assume that there is penalty in case if the branch happens. In case if the branch does not happen, anyway, since we are fetching the next consecutive instruction and executing it, there will be no penalty, right? So let's see how to analyze it. So assume that the questions in the exam will be asked like this. There will be a program containing 1000 instructions, out of which, let us say, 200 instructions are branch instructions, and let us assume that the output of the branch will be known only at the end of the last stage. Then they will ask us, what is the effective CPI, clocks per instruction? It is definitely not going to be 1 because of the added penalties. It has to be greater than 1. How much is it? So that all depends on the how we analyze it. So let's try to see how we can analyze such situation. Assume that we are having a program, and in this program, at various points, let us say these are all instructions in the program. The reason I am putting it in a figure is, you will understand it better if I explain you like this. Okay. Now say this is a big program and there are 1000 instructions in this, and you can assume that every row is an instruction. But then the problem is, the instructions which are branch instructions in the program will be spread across the program. They will not be at the same place, or it is not like all the branch instructions will be at one place and all the non-branch instructions will be at the other place. It is not like that. Okay, so you can think of it like this: branch instructions are present here and there. I'm just distributing it. So let us say there is a branch instruction here, there is a branch instruction here, one here, one here, one here, like that. Okay, here and there are branch instructions, whatever ticks I run. Now when you have such an organization, it is very difficult to analyze it. So what I suggest is, whenever you have branch instructions right, it is better you pull out all the branch instructions to one side and then put the remaining instructions in the other side, right? So which means you try to recreate the program in your mind as if all the branch instructions are in one side and all of them are going to execute one after the other, and all the non-branch instructions are on the other side. Got it? Now anyway, we know that for the non-branch instructions, CPI is always going to be 1, and whenever you have branch instructions, CPI is not going to be 1. That depends on when we are going to know the effective address. Okay, are you getting it? So now let us examine, if the program is containing only branch instructions, then what will be their CPI, clocks per instruction? Let's examine that, then you will understand it. Okay, now assume that we have a 4-stage pipeline, S1, S2, S3, S4, and the output of the branch will be known, which means the branch address will be known only at the end of the 4th phase, which means S1, S2, S3, S4 are the 4 phases, and the output of this, the target instruction address after the branch instruction is evaluated, will be available only after the 4th stage, assume that way. And therefore we are going to introduce the stalls after the branch instruction without executing it. Now 1, 2, 3, 4 clocks, right? So assume that, okay, let's put it another way. Assume that the result of the branch instruction will be known at the end of S2, which means after I execute stage 2, I'll be able to find out exactly what the next instruction is. Either the branch has happened or not. In case if the branch has happened, what its exact address is, then I can start the next instruction exactly at this stage, right? Therefore only one stall is there. Are you understanding it? In case if I am assuming that I will know the target address of the branch after the stage S2, right? Then I can start the next instruction, the exact right instruction, at this point in the third clock. Got it? Therefore I can start it like this: S1, S2, S3, S4, right? So this is a branch instruction and this one is also a branch instruction. See, whatever I am doing is not right practically, but just to make the analysis simple, I am doing this. Try to follow this. You will not, the textbooks will be explaining it in a different way. That will be confusing. Once you understand what I am doing it here, you will be able to answer all the questions very easily. Try to follow it. Now this is a branch instruction. This is also a branch instruction. Under the same assumptions, what is it? Branch is going to happen, and we'll be knowing whether the branch is going to happen or not, and the target address of the branch also after the stage S2, right? Then I can start the next instruction here. Therefore S1, S2, S3, S4. Similarly, the third one is also a branch instruction because we are executing only branch instructions, right? And again the same thing will happen. After this stage S2, I'll be able to find out the target address. Therefore here S1, S2, S3, S4, right? Now let's see what is the rate at which instructions are getting completed. See, this is clock 4, one instruction is over, and this is clock 5, clock 6, clock 7, clock 8, clock 9, clock 10. If you observe it, at clock 4 one instruction has come out, at clock 6 one instruction has come out, at clock 8 one instruction has come out, and clock 10 one instruction has come out. If you observe this one, for every 2 clocks one instruction is coming out, in case if you are able to find out the next instruction address after stage 2, right? Therefore in this particular case, the clocks per instruction for the branch instructions only, for the branch instructions are 2 when the branch is going to happen, and we are going to know the target address of the branch after the second phase. Got it? For the remaining instructions it is 1, for the branch instructions it is 2, right? Now what is the average? We have to count how many instructions are here, how many instructions are here, multiply them and then divide by the total number, right? Let us say there are 80 instructions which are non-branch and 20 instructions which are branch, right? In this case, what is the average number of this one cycles? So 80 instructions are going to take 1 cycle and 20 instructions are going to take 2 cycles, right? So this is the total number of cycles that are required to complete this, assuming, forget about the first instruction which is going to take n cycles, right? Over a long run, over 1000 instructions, that doesn't matter much. So this is the total number of clocks which are required to complete all the 100 instructions. Then what is the average number of clocks, which is nothing but divided by 100. So if you see this, it is going to be 120 divided by 100, I guess. So which is nothing but 1.2, which means the average clocks per instruction is going to be 1.2. Got it? So here I have taken certain assumptions. One assumption is that all the branches are conditional branches, and every time branch is happening and that particular target address is known after second stage. Under that conditions I evaluated this, but in the exam they will give you various conditions, but they will be very easy to understand and analyze. Once you understand this part, it is very easy. Once you understand how to analyze the clocks per instruction, the remaining part is very easy. It is just a kind of mix and match. It will be easy. Okay, so now let's see what happens in case if you know that the branch instruction address, the target address, if you come to know about the target address at the end of the third stage, right? Let's see this. So stage 1, stage 2, stage 3, stage 4, and now the assumption is that we will be able to know about the target instruction address only at the end of S3. Then what happens? Then we can start the next exact instruction only here, and these two are stops. We cannot start anything there. Assuming that a clever compiler is not used, then we are going to talk about this S4, and the next instruction will start here, right? S1, S2, S3, S4. Now if you observe it, 1, 2, 3, 4, and what is this? 5, 6, 7, 8, 9, 10, right? So at clock 4, one instruction has come out. Clock 7, one instruction has come out. Clock 10, one instruction has come out, right? Therefore, for every 3 clocks, one instruction is coming out. So average clocks per instruction in this case is going to be 3. In this case, when we are able to find out the address of the target instruction after stage 2, the average the clocks per instruction is 2. In this case, clocks per instruction is 3. Right? If it is given in the question that we will be able to find out the target address only after stage 3, then for all the branch instructions you should take the clocks per instruction as 3, because you have seen here, right? They are effectively coming out one every 3 cycles. And now appropriately you have to put the numbers there. I think you will get the answer as 1.4 if you substitute in the previous case, which is for 80 instructions the clocks is 1, and for 20 instructions the clocks is 3. Then out of total 100 instructions, what is it? It is going to be 1.4 clocks per instruction. Got it? So what about the other one? Let us say if you are pessimistic, and if you say that the exact instruction, the target instruction address will not be known till the last phase, until you finish the execution of the last phase, then what happens? Then S1, S2, S3, S4, then the next instruction can start only here, right? Which means S1, S2, S3, S4, and the next instruction can start only here, right? Now what is happening? For every 4 clocks, one instruction is coming out. Therefore, clocks per instruction in case of this one is 4. Appropriately you have to do this, right? And I think you are going to get 1.6 as the answer. 1.6 is the average number of clocks per instruction, or effective clocks per instruction is going to be 1.6. So in general, now we shall, if you understood how I did this, now we shall take an example, or we shall take a derivation using which we can derive some formula. See, I am going to derive some formula, but it doesn't mean that you have to by heart it. Okay, so if you understood this one, I think you will solve any question easily. Anyway, I'll try to derive some formula. Don't by heart it, try to understand that one as well. Okay.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So, first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and IITs, universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkee's ranking is 400. If you are happy to get into IIT Roorkee, then getting into universities better than IIT Roorkee is easier compared to getting into IIT Roorkee. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.